Hello everyone. Today we'll be starting a new module on control system 1, that is time domain analysis. Our today's topic is introduction to time domain analysis and step response of first order systems. What is learning outcome of today's lesson? That is understand the basic concept of time response of first order system. So before starting our discussion, let me tell you why shall we study time response analysis or time domain analysis of a control system. If you can remember, you have seen many bulbs to be turned on just after turning on the switch of the bulb. So just after turning on switch of the bulb gets turned on with its full intensity. But what happens in case of a fan, ceiling fan or table fan? Will you get the rated speed or maximum speed then and there just after turning on the switch of the fan? No, it will take some time. So with respect to time, bulb gets almost no time or very less amount of time to respond and to lit with its full intensity, to glow with its full intensity. But in case of a fan, it takes some time to get its rated speed or full speed. So why this happens? Due to time response nature of these electrical devices. So how a system respond with respect to time, that is to be analyzed. And how shall we analyze those? That will be discussed in this module, time response analysis module. So in today's topic, we'll be discussing how a first order system should respond with respect to time. So these are the topics to be covered in today's class. First, we'll be discussing about what is time response. Then we'll discuss about common input signals, because response means what? Response means with some input, how a system is responding. That means whenever an input is given to a system, an output should be produced. So what is nature of that output? That is to be studied in time domain analysis module. So what are the common input signals which are frequently used in control system analysis or in an electric system, that we need to know. So common input signals will be described. Next, what is order of system? As we have seen, we are going to discuss today time response analysis of a first order system. So what is order? How can you define order of a system? How can you identify whether it is first order or second order or higher order system? That will be discussed in third topic. Next, we'll try to find transfer function of a first order control system. Next, we'll move to step response of first order system. How a first order system behaves with a step input, that we'll be discussing. Next, we'll be discussing what are the effects of time constant on system speed or system gain on system response. All those will be discussed in today's class. So let us start with what is time response. Response means if an input is given, if an excitation is given to a particular system, how the system is producing output, what is nature of output, or how the system is responding, that is known as response. So with an input, a system should respond. Now, the response of the system may vary with time or may be invariable with time. So what is nature of the response? That will be discussed in today's class. So time response means how a system is behaving with respect to time. As we can see here, this is time response, or this is output graph of a first order system. What is first order system? I am coming into that later. But in circuit theory, you already have studied RL circuits are considered to be first order systems. RC circuits are first order, whereas RLC are second order system. So in control system, how can we define order? That I'll be discussing in next slide. As of now, let us consider this RL circuit, which could be considered as a first order circuit. Now for this RL circuit, whenever switch is turned on, a current will start flowing through this path. A current will start flowing through this path due to application of this voltage source. So whenever switch is closed, current is flowing. Now due to presence of this inductor, current cannot increase rapidly, so current will increase gradually. Current will increase gradually. After some certain time, the current will become steady. So this is the current axis and this is time axis. Now, total response of a system can be divided in two parts. One is known as transient response, another is known as steady state response. So what transient response is? See here, before turning on the switch, the system is at zero response, or magnitude of current is at zero. Just after turning on the switch, the state of the system response is changing. It is increasing slowly. So transient response is that part of the system response in which it changes its state. Okay, so transient response generally occurs during the starting period of switching. Now after some certain interval, after this interval, this time axis, so after this point, after this time, see, the output almost becomes steady. Okay, this is known as steady state response. Okay, so this part of the response is steady state response, as during this period or during this time the system response becomes steady or constant. So any system response can be divided in two parts. One is transient response, another is steady state response. Now let us discuss about the common input signals which are frequently used in electrical circuit analysis, in control system analysis. First signal is step signal. You all are familiar with step signal. Step signal can be described by these two equations: ut equals to 0 for t equals to 0, ut equals to 1 for t greater than 0, for t greater than 0. Okay. Now this is known as unit step. If it is a step signal of something k unit, then this magnitude would be k instead of 1. So unit step function could be described by ut equals to 0 at t equals to 0, t less than equals to 0. We could write this way: t less than equals to 0. So for this duration, see, this is time axis. So for this duration, time is 0 or less than 0. So during this time, the step signal will have 0 magnitude. Now at t equals to 0 and greater than t equals to 0, see here, at t equals to 0, the system suddenly steps up and it will move on. This magnitude here is shown as k. So a step function with k magnitude will be known as a step function with magnitude k. But if k equals to 1, if k equals to 1, then it will be termed as unit step function. So in control system analysis, we will be working with unit step function, because if system response for unit step function is known, then you could analyze that particular system for any magnitude of step response. Step function is an example of DC source, constant DC source. It's a constant value. So if at t equals to 0 switch gets closed, suddenly the DC voltage will appear. So before closing the switch, the magnitude of the DC is, magnitude of voltage across 1, 2 will be 0. So DC source is an example of step function, and as most of the systems are applied with DC sources, so we must know how to how a control system, how a first order or second order system behaves for such step functions. Now, what is Laplace transformation of unit step function? See, we know this is the basic formula for Laplace transformation, in which this ft could be replaced by ut, as we are going to find Laplace transformation of ut. Now, as for t less than 0, the unit step function is having 0 value. So this magnitude we could consider from 0 to infinity. So ut would be 1, and this will give us 1 by s. So for unit step function, Laplace transformation is 1 by s. Next, ramp function or ramp signal. Rt equals to 0 for t less than 0, Rt equals to kt for t greater than equals to 0. Now, k, the magnitude of k, when the magnitude of k equals to 1, it would be termed as unit ramp function. So for unit ramp function, it will be 1 by a square. Laplace transformation of unit ramp function will be 1 by a square, whereas a ramp function of k magnitude or k slope, then it will have k by a square as its Laplace transform. So all these are known to you, so I'm not going to go into elaborate details of this. Impulse function. Impulse function is a very short duration, high pulse. So for unit impulse, del t equals to 0. This del t equals to 0 for all the time except t equals to 0. At t equals to 0, del t equals to 1. Now, a unit step function, any unit step function this is a unit step function. Now, if I ask you to sample this unit step function into smallest part, then what would be sampled values? Like this. Like this. Now, this could be performed by a mathematical operator, that is differentiation. So in order to get the smallest part from an integral part, we must perform differentiation. So this impulse function is nothing but differentiation of unit step. That is why we can write this del t equals to ddt of ut. So Laplace transformation of del t equals to Laplace transformation of ddt of ut. Now, we know Laplace transformation of a derivative, that is s into Laplace transformation of ut. So Laplace transformation of ut is found as 1 by s into s, that is 1. So for unit impulse function, the Laplace transformation of unit impulse function will be 1. So these are the basic common input signals which we need to know to analyze a control system. Now, what is order of a system? Order of a system could be defined as the highest power of S in the denominator of its transfer function. As we know, we already have discussed that the control system analysis could be done in terms of transfer function based approach. So this is transfer function of a control system. Now for this control system, what is highest power of S in the denominator of this transfer function? Highest power is here. This is S to the power 1. So highest power of S in the denominator of the transfer function is 1 here. So this could be defining the order of the system. So for a first order system, number of poles should be 1, isn't it? Here the pole is located at S equals to minus 1 by T. So a first order system can be defined as the system in which highest power of S in the denominator of its transfer function is 1. Now the first order system should only have one pole. RL and RC circuits are examples of first order systems, and first order systems are generally expressed by this expression. CS by RS is the transfer function equals to K into 1 by ST plus 1, where K is the gain of the system, DC gain, and T is the time constant of the system. So what is DC gain? What's the effect of DC gain on system response? What is the time constant? All those we'll be discussing in next few slides. For example, suppose you have 2-volt input, you want to get 10-volt output. So what shall you do? You could put an operational amplifier working in inverting or non-inverting mode. If it is working in inverting mode, then 2 op amps are to be used in non-inverting mode. If you want to use only one op amp, then it has to be worked in non-inverting mode. Now what should be gain of that amplifier? You are having 2-volt at input, you want to get 10-volt at output, so the gain of the amplifier should be 5. So the DC gain is that one, that 5 is the DC gain. How much amplification you need to get the output from the input is known as the DC gain. Now transfer function of a first order system. So as we discussed, this is the general expression for transfer function of a first order system. The general expression could be written in this term as well. Now I'm telling you, here it is 1 by ST plus 1. Here it is K by ST plus 1. What's the difference between these two? See, if we consider the system is having gain of 1, forward path gain is 1, then we'll get 1 here. If it is K, if the system gain is K, then it will be K. Okay. Nothing else. So suppose the forward path gain is 1 by ST plus 1, 1 by ST, and it is having unity feedback. That is, unity gain is here at the feedback path. So what will be overall transfer function? 1 by ST plus 1. As it is connected in feedback combination, so this formula will be used to get overall transfer function as we discussed in block diagram algebra. So GS equals to 1 by ST, and GSH 1 plus GSHS will be 1 plus 1 by ST multiplied by HS equals to 1. So this will give us 1 by 1 plus ST. So this is general expression of a first order system transfer function if the system gain is considered as 1. Now what would be step response of a first order system? As we already have seen, a first order system transfer function can be represented by K by 1 plus ST. Now for step input, step response means what? How a system is responding due to application of a step input. So step response means due to step input, how the system is responding. So response due to step input, we are going to analyze now. For step input, as we know, RS equals to input will be 1 by S. So substituting the value of RS in this equation, we will get CS equals to 1 by ST into K by 1 plus ST. Now by performing partial fraction, we'll get CT equals to this. This is a simple partial fraction involved here. Now, what we have got now? We have got this equation. This is CT. CT means output in time domain. So as we are going to analyze time response of a system, so this is the response of the system, CT, or output of the system, and this is the time axis. So how the output is changing or responding with respect to time, that we are going to discuss now. The graph drawn here is entirely based on this equation. Now see, e to the power minus t by t, this is exponentially decaying term. So 1 minus exponentially decaying term will be exponentially increasing. That is why nature of the graph is exponentially increasing. Okay. Now, if t equals to 0, in this equation, if t equals to 0, then e to the power 0 will be 1. So 1 minus 1 is 0. So at time t equals to 0, output will be 0. Okay. Now, if time is very large, after a long time after switching, t tends to infinity. So e to the power minus infinity will be 0. E to the power minus infinity is 1 by infinity, that is 0. So 1 minus 0 is 1. So CT will become now K. Clear? So CT equals to K when time approaches infinity. So when time is very long, after a long time after switching, this length is K. Why this is K? That I'm going to discuss. Okay. So when time is 0, output is 0. When time is long, then output will be K. Now, let us assume K equals to 10 and T equals to 1.5 seconds. So what will happen? This is 10. As we have seen, when time approaches infinity, the CT will be equals to K. So as you have assumed K equals to 10, so this response curve will reach 10 after a long time. Now, when small t equals to capital T, when small t equals to capital T, what will happen? This equation will become if small t equals to capital T. So at small t equals to capital T, this equation will become this. So 1 minus 0 minus 1 will be 0.632. Okay. So at small t equals to capital T, here capital T is considered as 1.5 seconds. So at 1.5 seconds, at this point, this is 1.5 second. At 1.5 second, the system reaches 63.2% of final value. Okay, 63.2% of K. Here K is 10, so 6.32 it should reach. So 6, this is 7, 6.32 is reached. Okay. So this T is known as time constant. So time constant is this much time. This much time is required for the response curve to reach 63.2% of the final value. So time constant can be defined as the time taken by response curve to reach 63.2% of final value. And what is DC gain? DC gain K equals to steady state output. Steady state output is 10 divided by input is what? Unit step input is given, so input is 1. So DC gain should be 10. Okay. Now, see what this shows in different time constant, how the system is responding. In first time constant, when small t equals to capital T, the system reaches 63.2% of final value. At 2 time constant, it reaches 86.5%. At 3 time constant, 95%. At 4 time constant, 98.2%. And 5 time constant, 99.3%. So all this we could get by substituting small t equals to capital T, small t equals to 2t, small t equals to 3t. So depending on this small t, we'll get the response curve. So this entire response curve and this entire percentage is obtained from this equation. Okay. Now, a system is said to be reached at steady state value if the system reaches 98% of its final value. That means if a system has not reached total 100% of the final value, a system may not reach. What we can consider 2% basis calculation. For 2% basis calculation, we can say if a system reaches 98% of final value, then the system is stable. So here, to reach 98% of final value, it takes 40 time. So 40 time is known as settling time, the time taken by response curve to get settled down to a steady value. For 5% basis calculation, 3t time is taken as settling time. If much accuracy is not needed for a particular system, in that case we can consider 5% basis calculation. In 5% basis calculation, we could say a system is at steady state or system output is settled down if the system reaches 95% of its final value. So settling time for 2% basis calculation would be 40. Settling time for 5% basis calculation will be 3t. Now, what is effect of time constant on system response? That means if time constant goes on varying with a constant DC gain, then how system response would be varied, that we are going to discuss now in this slide. See here different time constants are taken. For time constant 1 second, 3 second, 5 second, 7 second. So which one is responding faster? This one reached around 63%. This much time is taken by first graph, blue colored graph, to reach steady value, to reach 63.2% of final value. Let us mark it with blue color. Okay. Next response curve reaches same value, 63% in this time. Next one reaches 63% in this time. And the last one reaches 63% in this time. So what can we conclude from this? First one takes very less time, blue one takes very less time to reach at 63.2% of its final value. Second one takes some more time to reach at 63.2% of its final value. Third one takes more larger time. Fourth one takes again much larger time. So the conclusion is, as the time constant is increasing, the system is taking more time to reach a particular value, which implies as time constant goes on increasing, the system speed is slow, system takes more time to respond, or system response becomes slower. Now, if you can recall, time constant of RL circuit is T equals to L by R. For a constant R, if L increases, time constant will increase. And what's the effect of L? As L increases, it will current will take more time to increase. L opposes rate of change of current. So more the value of inductor, lesser will be speed of current. Okay. So that is how time constant affect system response. Now, what is the effect of gain for a particular time constant on a system? If gain is 1, then the response output reaches 1 magnitude. If gain is 3, output reaches 3 magnitude. As input is unit step, so depending on the gain value, output will be 1 or 3 or 5 or 10. So simply we can write this at steady state. So ut is 1. So if k equals to 1, system gain is 1, then output will be 1. If system gain is 3, output will be 3, 5, 5, 10, 10. So if you require more output, then system gain has to be increased. There are some drawbacks of increasing system gain. So what are those drawbacks? That we'll be discussing later while designing controller section. So as of now, today I'm ending up here. Let me summarize the entire part which we discussed today. We discussed first what is time response, what is order of a system, what are the common input signals applied to a control system, or what are the test signals which are used to analyze a particular control system. What is step response of a first order system, how system respond with respect to time if step input is applied, what are the effects of time constant and system gain, DC gain on system response. All those we have discussed. In next class, we'll be discussing about impulse response and ramp response, other two inputs. For the other two inputs, how the system is responding, that we'll be discussing in next class. So as of now, I'm ending up here. Thank you all.